Hello, everyone. Hopefully, you're doing well. After we go over chapter one, equations and inequalities, chapter two focus on functions and graphs. Of course, you graph a variety of functions already, but we're going to talk about really what is a functions. But you know what? Functions are something you already know. So functions of salary, we can have a function expressing salaries. That means if you know what is your hourly wage, then you know, for example, a function f of x, where x represent the number of hours you work. Suppose your hourly wage is $15, so your functions representing your income is 15x. 15 is a constant because that would never change because it's your hourly wage. X is the number of hours you work. So we're going to go over some basic functions very quick in section 2.1, basics of functions and the graphs. And in a different video, we're going to go over like more functions in the graph, linear functions and slopes, transformation of functions, combination of functions, composite of functions, inverse of functions, and we would conclude this chapter with distance and midpoint formulas and circles. But as I said, in this chapter, we would focus on basic of functions in the graph. We're going to find the domain and range of a relation, determine whether a relation is a function, determine whether an equation represents a functions. We're going to evaluate the functions, graph functions by plotting points. Of course, that's something we've been doing for a while, but we're going to focus on details on this one. So use the vertical line test to identify functions. When you draw a vertical line over a graph, if it's intersected one times or two times, it means something at least one times or the most one times. We're going to see this. Obtain information about a function from its graph. We can give you a graph and ask you to answer questions. For example, you have a graph representing the population of a certain city over a period of time. So we can give you the graph and we said, what is the population of that country, of that city in a very specific year? So you should be able to identify that. We're going to identify the domain and range of a function from its domain, and also identify intercepts from a function. A lot in one section, but don't forget, we're gonna go very quick on this. So the mathematic terms for a set of ordered pairs, we call it a relation. Like any times you have in ordered pairs. For example, if you have, when I said ordered pairs, for example, if you have the first one is the x coordinate, the second one is y, if you don't want to call them x and y, as long as you put them inside of a parenthesis, it means something. For example, I can say John, all right, 6. So it all depends of what I mean by these two coordinates. I might say John has 6 children, or John has 6 siblings, or I can say John works 6 hours. It all depends. But the most important is to remember what each coordinates represent. The first one we're going to call it independent coordinate. The second one, we call it dependent, right? For example, when we said, uh, you know, your salary is 15x, that is 15 represent the hourly wage, and x is the number of hours. When we have that, that's what we're gonna call. So it's the same thing calling f of xy equal 15x, right? So if we have that, y is dependent because it change every time x change. If x never change, y would never change. So if you work only 2 hours, suppose x equal 2, so you work 2 hours, what would be your hourly rate? What would be your income? So it'd be 15 times 2, that make it 30. But it would be rare that you go to work for only 2 hours. I suppose you work for 10 hours, right? So your income would be what? Yes, 15 times 10 is 150. So that's mostly what we're gonna cover in this section, telling you about relationship and functions. I'm going to erase all of this because I think I jumped into heavy materials before we even define a relation. As I said, a relation is in any set of ordered pairs, right? You can find it everywhere. The set of all first components of the ordered pairs is called the domain. For example, as I said, if we see John 6, so a domain is John and the second one, okay? And the set of all second components is called the range of the relationship. For example, you know, X would always be the domain, or we can say it's first component, and Y would be the range. So domain is all about the X values, the first components, and the range will be all about the Y value. So as I said, that's what we're gonna talk about in this case, all right? Now, before we even get further than that, you know, we can even go over some examples. What do you think? All right, let's do some examples. In these particular examples, as you can see here, we said, you know, find the domain and range of the relation, right? So they said first component is the domain, second component is the range. So we can say the domain is the set of all first components. So what's the domain? If you remember, look at here, what would be the first components? We're gonna make a list of all of them, okay? The first components, yes, we have 0. In the second ordered pair, we have 1. In the third one, we have 2. In the fourth one, we have 3. So that's a set of all the set of all first components. The domain is this. Now we remember the range is the set of all second components, right? So if we go with the range, okay, so remember range is the second component, so we can go, the range would be 187, 212, 225, 238. Okay, so yeah, that's how we're gonna go with these examples very quick. Okay, so of course plenty of things you can do with a relationship, you know, with relation, not relationship. All right, so but we also can talk when we have those type of relations, it's gonna bring us to something else you probably see before, because in relation in which each member of the domain correspond to exactly one member of the range is called a functions. So that's what we're gonna talk about here, because a function, something you see before, we need to go over how you can set those relationships. For example, in the previous one, if you decide to put all the domains together, for example, you know, 0, 1, 2, and 3, you know, each of them correspond to only one, right? To 12, to 25, and to 38, you see? Only one. So each of them goes to 1. And to do that, we said a function is a corresponding correspondence from a first set called the domain to a second set called the range, such as each element in the domain corresponds to exactly one element in the range. As we said, a relationship in which each member of the domain corresponds to exactly one member of the range, we call it a function, right? That's very important. For example, you can see each element in each first component in the previous example correspond to exactly one component in the second example, okay? So a function is a relationship in which no two ordered pairs have the same first component and different second component. So I'm hoping you, you can remember what I said, or just stop the video and review it again. I know it's very important to you to see that. Now, if we look at these examples, so the first one, what they ask you to do, they said, determine whether each relation is a function. So in order for me to verify if each relation is a function, I need to verify if each member of the first component correspond to exactly one member to the second component. So I can do it different ways. For example, if I go with A, I can do, okay, you know what? I call this one 1, 3. Okay, 1, 3, 6, 8. That's the first component. I'm gonna call it X, right? Just a name. And the second one, second components, we have 2, 4, 5. I don't need to put 5 twice. Even though they put it twice, I don't need to put it twice. So this is the second one. I'm gonna call it Y, okay? So I know 1 goes to 2, 3 goes to 4, 6 goes to 5, and 8 goes to 5. All right, determine whether the relationship is a function, right? So you can verify this one. Every element of the domain corresponds to exactly one element in the range. Remember, even though 6 and 8 goes to the same elements in the domain, but no 6 goes to you don't have 6 goes to two different elements in the range. So because every no ordered pairs in the given relation has the same first component and different second component, so we would consider this one as a relation. That would be this relation is a function. So relation is a function. But as I said, not all the time. You might have it different ways. If we go, for example, with B, let's try B. You see B, we have first components 1, 3, and 5. So let me call this one X. And the second component, we have 2, 4, okay, 6, and 8. Okay, that's the second one. Now, let's call it Y. Okay, first component, 1 goes to 2, agree? 3 goes to 4, and 5 goes to 6, all right? And you see, 5 also goes to 8. Is this relation a function or not a function? You need to verify if it's a function or it's not a function. All right? So because 5 correspond to both 6 and 8, if any element in the domain corresponds to more than one element in the range, the relation is not a function. So this relation is not a function because two ordered pairs have the same first component and different second component, right? So now we would conclude that relation is not a function. I'm hoping you get that one. And of course, you can continue to do more examples with that one, all right? If you have questions, you let me know because we're gonna enjoy doing those type of examples. Now, functions as talking about relations as functions, but we can say also functions as equations. So if we have, if an equation is solved for y and more than one value of y can be obtained for an x, sorry, then the equation does not define y as a function, right? Not all the time it's going to be a function. So functions are usually given in terms of equations rather than as set of ordered pairs, because we use ordered pairs just to explain what we're doing, but usually give me 1 second, please. All right, so sorry, I was getting some water. I'm hoping that's not a problem. Functions are usually given in terms of equations on a set of ordered pairs, all right? For example, usually we have the functions like y equal f of, f of x is y. So I can either say y or I can f of x. So if we have 2x plus 5, right, that's a function, right? But the variables x, as we said, representing independent variable. The x represent is called independent variable because it can be assigned any value from the domain. X can be assigned any non-negative number, integers, or or negative integers. All depends. The variable y is called the dependent variable, right? Because its value depends on x. Dependent means values depend on x, right? So the value of the dependent variable y is calculated after you select a value for independent variable x. So we have seen that not every set of ordered pairs define a functions, right? Similarly, not all equations with the variable x and y define a function. So if an equation is solved for y, more than one value of y can be obtained for a given x, then the equation does not define y as a function. So that's why we wanted to go with that examples, but we're gonna expand this into an example. So let's do this instead. Yep, right there. We said solve each equation for y and then determine whether the function define y as a function of x. Look at the first one. You have y squared. All right, we have y squared, x squared plus y squared equal 1. All right. First of all, what you need to do is, we can solve for y. Okay. So if we take a, we said x squared plus y squared equal 1. If we subtract x squared from both sides, y squared would be 1 minus x squared. So I just jump into one expression. We isolate the y squared by subtracting x squared from both sides. Then if it's possible, we can simplify. Unfortunately, there is nothing to simplify here. And what you need to do in order to obtain the y values, remember it's power 2, we take the square roots of both sides. So y would be plus and minus square roots of 1 minus x squared. Remember, we call it plus and minus, all right? The plus and minus in this equation shows that for certain values of x, all right? For certain value of x, remember x cannot be more than negative 1 and 1, okay? Because if it's negative 2, or positive 2, it's gonna be undefined. Remember that, because you cannot take the square root of a negative number. There are, for the plus and minus in these equations indicates that for certain values of x, there are two values of y. Because we said plus and minus, there are two values of y. Then this function, for this reason, the equation does not define a function. So, okay, that's it. This is not a functions. Okay, so I explained why it is not a function. The plus and minus shows that for certain values of x, there are two values of y. Remember, we said plus and minus. So for this reason, it is not defined a functions. But let's go over B, okay? So if we do B, we have 2x plus y equals 6. Now remember, you must solve for y. So if we subtract x to both sides, we're gonna have y equals 6 minus 2x. Ah, look at this one, how that's work, okay? So for this one, all right, because every times, uh, we can see that for each value of x, there is one and only one value of y, right? Anytime if x is 0, y is 6. If x is 1, y is 4. If x is 2, y is 2, all right? If x is 3, y is 0. If x is 4, y is negative 2, etc. So we're gonna continue this way because, all right, there is only, for each value of x, there is only one and only one value of y, all right? So we would conclude this equations, y is a function. So y is a function, or we can say this equations. Remember, an equation is a statement that two algebraic equations, two algebraic expressions are equal. So we can, as long as we have an equal sign on both, in between two expressions, we call it equations. All right. So we're gonna go over this one now. Function notation. How do we know? If an equation in x and y gives you one and only one value of y for each value of x, then the variable y is a function of the variable x, right? Okay, the variable y is a function of the variable x. So when an equation represents a function, the function is often named by a letter. So we can call them F, G, H. We can call it by my first name, first letter of my first name, N, as in Nancy, N of X, or G of X, all right? Or you can call, if your name is John, so J of X, you can give it in, all right? So no problem to calling any letter can be used to name a function. So, suppose that F names a function, then think of the domain of the set, of this, the domain of the set, the domain as the set of the functions input and the range as the set of the functions output, right? So the special notation f of x with f, the special notation f parenthesis x, read f of x or f at x represent the value of the function at the number x. For example, if x is your input, x is the input, f of x is the output, right? So that means enter x each time. If I have a function f of x equal 2x plus 3. So if x equal to, what would be y, f of x? All right, it would be f of 2 equal 2 times 2 plus 3, give you 4 plus 3 is 7, right? Very easy to see. Very easy to see. So you only need to verify and make sure that everything is correct on this one. Now, this is an example. What you do with a functions? We start doing a lot of things with the functions, among them evaluating functions. Anytime you have a functions, one of the things you can do with a functions is evaluate them or graph them. If you know the value for the independent variable x, for example, you see x equal -5, we would say f of -5. You just need to plug that number in the functions. So x -5, so -5 power 2 minus 2 times -5 plus 7. Okay, what you see here should give you 25 plus 10 plus 7. So you would conclude 25, what you said. What do you think this one would be? So f of -5 would be 25 plus 10 is 35 plus 7 is 42. Yay! way, right? Now, for some of them, it might be longer, right? For example, if you have some of them, like B, where we said find f of x plus 4, that means everywhere we see x, we replace it by x plus 4 square minus 2 times x plus 4 plus 7, right? So now, can you remember what we learned in the previous chapter? If you have a plus b square, we said raise the first one to power 2 plus 2 times the first one by the second one plus the second one power 2. So if I raise the first one power 2 plus 2 times the first one by the second one, 2 times x times 4 give you 8x plus the second one power 2, 4 power 2 give you 16. We're done with the first parenthesis. Now with the second one, we need to distribute the negative 2. Negative 2 times x give you negative 2x. Negative 2 times 4 give you negative 8 plus 7. Okay? What it is, next step is to simplify. Anytime you need to simplify, all right? Simplification, okay? Very important. The x squared is the only term we keep it. And we see 8x minus 2x give us 6x, right? We have 6x. 16 minus 8 is 8 plus 7 is 15. And this is it. All right. Now, if you look at C, where it says f of negative x, everywhere you see x, replace it by negative x in the original equations. Negative x power 2 minus 2 times negative x plus 7. So it gives you any negative number raising to to power 2 become positive, or any negative number with an exponent even, like power 2, power 4, power 6, power 8, etc. would be positive. So negative x power 2 give you positive x squared, and negative 2 times negative x gives you positive 2x plus 7. Nothing to simplify here, so we would conclude this. As you can see, the first one give us a real number. The B and C give us an expression because we don't know the value of x, but we can always substitute for it. All right? Questions about it? No, you're not here to ask me questions, so feel free to contact me for any questions and I'll be happy to answer them. Let's talk about graph of a functions. It's a little bit tricky when we talk about graph. You know, the graph of a functions is a graph of its ordered pairs, right? That's the best thing we can say. For example, the graph of f of x equal 3x is the set of points x and y. Remember, the first coordinates, you have x and y. If I have f of x equal 3x, all right? In the rectangular coordinate system, it's like we have y equal 3x. Every time you give values to x, all right? And to find what is y, okay? So every time you do that, you're gonna do it. Now, in the previous examples, we evaluated functions. Here, we ask you to graph that functions. You only need to find a set of ordered pairs. You know, you don't have a limit of how many ordered pairs you need to find. You know, if you have a linear function, 2 points is enough. But sometimes in some exercises, they can give you this all the first components and ask you to find the second components that would be on the graph. For example, here, they ask you to graph the functions f of x equal to x and g of x equal to x minus 3 on the same rectangular plane. So, you know what? Suppose I'm going to do it this way. I would assume this is my xy plane, okay? Call it different names. You can call it rectangular coordinate system, or I can get Cartesian coordinate system, or I can say XY plane. That's it. Remember, it's intersect at the origin. You know, that's the origin. If you go to the right, that would give the positive numbers, right? If you go to the right, that would be all positive, right? If you go on the left, it will be all negative on the x-axis. I'm gonna just do one if you understand. And if you go above, okay, let's go above these points. We're gonna go above these points. So let's go like above would be 1, 2, 3, 4, 5, etc. Below would be -1, -2, -3, -4, -5. If you don't get it, please feel free to. You know what I'm gonna do? I'm gonna use a different color for this. All right. Let's suppose if we need to do f of x equal to x for this graph, what I want to do here is to make sure for this graph right there, I find some points. They don't, oh, they said do it between -2 and 2. That's what I was talking about. Sometimes they tell you how they want you to do it. What would be the first components, and use the first component they give you to find the second one. Let's suppose here with these components, we're gonna construct a small table x and y. They said select integers. Okay, they said select your integers starting -2, ending with 2. That means we do -2, -1, 0, 1, and 2. Now, let's try. If you plug x equal -2 in the functions, you have f of -2 in the first function. So 2 times -2 give you -4. So we know this one will be -4. All right. 2 times -1 is -2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. You see? No first component give you 2 different components, right? So it gives you exactly 1 component, all right? So now our first coordinates, if you want, you can rewrite them as -2, 4, -1, -2, 0, 0, 1, 2, 2, 4. If you want to write it that way. So what I'm gonna do, -2, x -2, I'm gonna have the most beautiful -4 here. So 2 give us -4. Okay. -1 give us -2. All right. 0 give us 0. 1 give us 2. And 2 give us 4. So if you want, that will give me a very straight line. I mean, I sketch it. Remember, I do it with a tablet, so it might not be that straight. You see, I put it indefinitely. But if I don't want to do it this way, because they said, you know what, do exactly from -2 to 2. So sometimes I can just go ahead and not putting it goes indefinitely. So instead of putting an arrow at the end, you know, I can erase it. I can erase the arrow. Oops. I do exactly from this point to this point, okay? Now, let's go with the second one. I'm going to erase everything. Let me erase that table. I mean, not the table. I'm using erase the coordinates. I'm gonna do the other one in red. I know you might like red. So f of x equal 2x minus 3. Now we're going to graph again xy, -2, -1, 0, 1, and 2. Okay. They don't say f of x, they call it g of x. Sorry about that. So that's f of x equal to x. So that was this graph. Now for the second one, x equal -2. 2 times -2 is -4 minus 3. That's give you a -7 if you see it, right? 2 times -1 is -2 minus 3. That gives you a -5. 2 times 0 is 0 minus 3 is -3. 2 times 1 is 2 minus 3 is -1. 2 times 2 is 4 minus 3 is 1. Right? So far, that's what I have. So when x is equal to -2, y give me a -7. So unfortunately, I might not see it, but it's all the way down here, right? When x is -1, y give me a -5. I'm gonna keep it that way. When x give me 0, y give me a -3. This is -3 right here. When x give me 1, y give me a -1. Okay? And when x give me 2, y give me a 1. So if I graph that line right here, this is it. Of course, I can continue indefinitely if I want, but otherwise, I can leave it like that, or I can continue to it. So remember, this graph right here is g of x equal to x minus 3. All right? If you're okay with that, I think that sounds pretty good as an example that you can really enjoy. All right. In these sections, we have plenty of other things we can do, especially after you graph, we can talk about the vertical line, the vertical line test. So because not all the graphs you see is a functions, right? So not every graph in a rectangular coordinate system is a graph of a functions. In order to decide if a graph is a function, definition of a function specify that no values of x can be paired with 2 or more different values of y. So you would never find 2 different y's for the same x. No 2 different y's for the same x. All right, so that's not going to happen. You cannot find it. Even though, remember, if you said if you have x equal 2, even though the functions is x squared, x squared minus 1, you're gonna find exactly 1 y for it. Okay, you're gonna find 1 y for it, so it's not gonna happen. Now what we said then, all right, so what we said, sorry, if a graph contains 2 or more different points with the same first coordinate, the graph cannot represent a function, right? So if any vertical line intersects, that's why we said that the observation is the basis of a useful test. We call it vertical line test for determining whether a graph define y as a function. So the test, as I said, is called vertical line test. So if any vertical line intersect a graph in more than one point, the graph does not define y as a function. So if you have a graph, any graph you see, I'm gonna show you. If I have a graph like this, okay, suppose I have a graph, where I am with that. Okay, I think pencil die. Give me a few seconds. I need to connect it and make sure it's working. Okay, I'm gonna keep it connect because my pencil die on me very quick. Okay, suppose I have a graph like this. Okay, we're gonna learn what type of graph is this one later, but for now, just focus. If I have a vertical line that intersects the graph anywhere only one time, only one times, we said this is a graph of a function. But suppose I have another graph. Let's suppose I have another graph like, okay. So you see, vertical line would intersect my graph more than one times. Because this would intersect my graph more than one times, this one is not a graph of a function. So that's why I need to verify and make sure we all agree on that. So examples, look at these two. Use the vertical line test to decide to identify graph in which y is a function. If I call this one A and I call this one B, so which one you think is a function and which one is not a function? Yes, the first one is a function. Why? Because if you draw anywhere, if you draw a vertical line, it would intersect your graph only one time. You see, everywhere you go a line, it would intersect your graph one time. But this one not a function because if you draw a line, you see it's gonna intersect your graph two places, more than one time. So you would conclude that the first one is a function, the second one is not a function. Of course, you're gonna have plenty of homework to complete with that one, all right? Please verify that anytime you have a chance. One of the things we do with graph is obtaining information from the graph. I told you already, you can obtain information from a graph. You can obtain information about a function in its graph, for example, here on this particular graph, they ask you to use the graph to find f of 5, right? I think if you look at this graph, a closed dot and a closed dots, you see these dots right there and right here indicates that the graph does not extend beyond this point and the point belongs to the graph. If it was open dot, so that's not the case here because this is, closed dot, indicates that the graph does not extend beyond this point and the point does not belong to the graph. So if we had that case, but that's not the case. An arrow indicates that the graph extends indefinitely. So when you have a graph, for example, if I have a graph and I put arrows like this, that means continue indefinitely. All right. If I have a graph, suppose on the XY plane, that's not the XY plane. I'm terrible in doing XY planes. Okay, this one, right? If I have a graph and I put it like this, you see? In the positive way, on the first quadrant, it says stop at that point. It's not included, but in the third quadrant, it says, oh, you know what? This point is included because it's a closed dot, It's like a small zero that we filled. So a big dot, not a small zero. All right. If you're good with that, let's answer the questions they just asked us. The questions, they said find f of 5. First of all, on the x-axis, you need to identify what is x of 5. That means for what value of x, all right, f of 5. So that's what you need to do. This is f of 5. I mean, x equal 5. So for what value of x, okay, you're good with that? All right. So we're gonna do that. F of 5, we go 5 up there and we project it on the y-axis. If you agree, maybe you would understand f of 5 is 400. Now, for which value of x? Y is for which value of x? Y is 100. So this is 100 would be half of this one, right? So what should be x? You can project it and go all the way to the graph. Oh, some of you might say this x is 9, right? All right, so that means x is 9. For this one, x is 9. That means f of 9 equal 100. So x equal 9. Okay, for what value of x? That means you can obtain any information you want from a graph with no problem. Okay. Another good things to learn in this section. There are plenty of things we can learn. We can even ask you to estimate something that is not in this graph, probably what would be 15, or, not easy to do, but you can still try, right? Domain and range from a graph, you can see it also. To find the domain and the range from a graph, we can definitely do that as well. To find the domain of a function from its graph, look for all the inputs on the x-axis that corresponds to a point on the graph. So we can do that. And to find the range of a function from its graph, the range, look for all the outputs on the axis that correspond to the point of the axis. So I think something you can really verify here, for example, in this one, I'm sorry, it doesn't move. Okay, right there. We said for this graph, you can see it, use the graph of the function to identify the domain. Look at the domain, right, to its functions. So what would this be the domain here? Oh God, okay. I can say domain. Please, for the domain, as we said, to find the domain of a function from its graph, look for all the inputs. What would be x's? Okay, see, this is the domain. X goes all the way to 1. So, do you have closed dot or open dot? Yes, you have closed dot. That means x can be 2, -2, x can be from -2 to 1. Anything from -2 to 1 would be the domain. So x, we can say the domain is x such that x is from -2 to 1. You see, I put less than or equal to because we have a closed dot. Look at the closed dot right there. Closed dot, right? So that means the endpoints is included, right? Are included, all right? So that would be the domain. Domain is all about x. If you look at for the range, now look at for the range, we said look for the outputs on the y-axis that corresponds to the point on the graph. Now, if you look at this one, right? Okay, I'm gonna use this one. You see, I would say y start here because the graph over there and goes all the way to here, right? So that means it's from 0, x such that x is, I mean, not x, sorry, I was supposed to call it y. I'm talking about y because it's about the range. Y would be between 0, from 0 to what? 3, yes, because that number here is 3, okay? So that's how we identify the domain and the range from a graph. We can also try different examples, like here, use the graph of the functions to identify its domain and its range. So we see here again, we start with the domain here and goes all the way to here. So what is that? -2. The domain, remember domain is about x, such that, now is would x be between is that close? The same one or not? No, it would be -2, but this one is not close because there is a hole. You see there is a hole, so it's a open dot because here it's open, so it's strictly less than a -2 less than x less than or equal to 1 because it's a closed dot right there, okay? So you're done with x, you can do the same for y. As you can see, y start at -1 and goes all the way to 2. So range X, that's y such that y would be between what again? We need to decide where we're gonna start. Remember, it's the -1 we go first, and it's less than or equal to, and we go up to 2. Okay? Or you can write them the other way around, you know. If you don't want to write it set builder notation, you know this one right there is -2, 1 for x, and for y it would be -1, 2. That's fine. And the previous one, if you want to use interval instead, interval notation, because we learn how to do it interval notation or set builder notation. This one, if you want, you can rewrite it as -2, 1. See, close. We use bracket, or we use 0, 3. No problem using bracket to answer those questions. A lot of things we can learn from this chapter, especially we can identify intercept from a functions graph as well. You know, wherever it's intersect with the axis, we call it intercept. The x-intercept look at the points at which the graph crosses the x-axis. Y-intercept, you look at the point at which the graph crosses the y-axis. So a function can have more than one x-axis, but at most one y-intercept. Remember that if it's a function, it can touch the x-axis multiple times, at least one of them, or maybe none. It all depends. But for y, it should be only one time. Okay, otherwise it's not a function. So what are the intercepts? So if we look at x-intercept, please look where the graph intersect with the x-axis, here, here, and here. What are those points, please? Yeah, the x-intercepts, we would say it's -3, or you can say -3, 0. And you have -1, 0, or you can say just -1. And you have the third one is 2, 0, or you can just say that. So y-intercept, is there anywhere you see your graph intercept with the y-axis? Yes, it's intercept with the y-axis, that one here. Now, is easy to see? Do you agree it would be 6, right? Yes, it's intersect at 6. So we're gonna say 0, -6. Remember, when we deal with y, second coordinate is y. First coordinate is x. Okay? Hopefully you learned something from these sections. Of course, that will be the first section of chapter 2, basic functions and their graphs. We're going to come back for more on functions in graph because there are so much to cover in section 2.2. Let me know if you have any questions. I'll be back for more examples. Take care.